There are different kinds of equations. A molecular equation is what we tend to think of as a regular chemical equation. It shows the complete neutral formulas for every compound in the reaction. And this is the kind we usually write. But there are also two other kinds that we use sometimes. A complete ionic equation shows all of the soluble ionic compounds as ions. So it's showing what's actually happening in the solution. So when you're writing the complete ionic equations, you're going to separate only the aqueous ionic compounds into their ions. Something that's insoluble does not dissolve into ions. It doesn't dissolve, and so you leave those alone. If there's anything that's a solid, a liquid, or a gas, you just leave it alone. You don't separate it into ions. And then we have something called spectator ions. And so sometimes I talk about the boxing match, but let's stay with the party idea. So these two couples went to the party and two of them got involved with each other. What happened to the other people? They're just standing around, watching. They did not get involved in a relationship. They didn't get involved in the chemical reaction. We say they're spectator ions. They left in the same condition that they came. And so nothing happened to them. So sometimes we're just not interested in what the spectators are. We're just focusing on what the reaction is. So we simplify the equation by getting rid of the spectator ions. And what we have as a result is the net ionic equation. This is like your net paycheck, right? The gross on your paycheck includes more stuff, but then they take out stuff for taxes and for this and for that and the other thing, and the net is what you actually get to take home. The net ionic equation shows only the things that are actually participating in the reaction. And when we use the word species, this is chemistry, not biology. When a chemist says species, we just mean a kind or sort of thing. Here are all the molecules and ions, because it can get a little tedious to talk about atoms, ions, and molecules, and so we just say a species. So consider this reaction occurring in aqueous solution. So we've got 2HBr plus CaOH2 forming 2H2O liquid and CaBr2 aqueous. Write a complete ionic equation and net ionic equation for the reaction. So I'm going to give myself a little more room by crossing that part out, because I can. So the complete ionic equation, what we need to do is we need to look at everything that says AQ, and if it says AQ, we're going to separate it into ions. So we're going to break this into ions, we're going to break this one into ions. We're not going to break the water into ions because it's a liquid. So only the things that say AQ. So HBr, we have to be able to take this apart into ions. Usually for the complete ionic equation, I leave the state symbols off because it gets really long and it doesn't fit very well. So I'm going to leave them off. So HBr is H plus and Br minus. And there's two of them, so we're going to get two H pluses and two Br minuses. If we have two of these guys and we break them into ions, we're going to get two of the positives and two of the negatives. And then over here, we've got one calcium hydroxide. This has one calcium ion and two hydroxide ions. So I've got calcium with a 2 plus charge, and I've got two OH minus. Now I get to this guy. This is a liquid. I'm going to leave him alone. Don't do anything to him. Just leave him alone. And then the last one is aqueous. So I have to separate this into ions. I've got calcium and bromide. There's two bromides. So calcium and bromide. It got smaller and smaller. You don't have to carry the coefficients down when you first break these into the ions, but if you don't do that, then later you have to go back and balance it again. If you're careful about carrying the coefficients down, then it'll be balanced when you're done. So here I've got 2 hydrogens on this side, plus this hydrogen here, 2 of them. So a total of 4 H's on the left, and I've got 2 times 2, 4 H's on the right. I've got 2 Brs and 2 Brs. I've got 1 Ca and 1 Ca. And I've got 2 oxygens and 2 oxygens. So this is balanced. So that's the complete ionic equation. The net ionic equation, I'm going to cross off everything is the same on both sides. So do you see this 2Br minus? There's a 2Br minus exactly the same on the other side. So I'm going to cross those guys off. They didn't get involved. I'm just watching. Nothing happened to them. Are there any other spectators? The calcium. There's a Ca2 plus on that side and a Ca2 plus on that side. They did not react. They're there, but they didn't react. And then I just copy down everything else. Usually at this point, I will put the state symbols back in. The complete ionic equation is rarely requested outside of this chapter. But it's a means to the end, which is the net ionic equation. So we've got 2H plus, those are aqueous, and 2 hydroxide ions, those are aqueous. And that's going to form 2 water molecules, and those are in the liquid state. I'm just taking these up here, bringing them down. And so this is our net ionic equation. That shows us what's actually occurring. If hydroxide had brought a different date, maybe hydroxide brought sodium instead, this reaction would still occur. It's this reaction between the hydrogen ions and the hydroxide ions forming water. Calcium and bromide had nothing to do with it. Any questions?